looking at the absolute bedrock of reality.
Yeah, the really fundamental scale of the quantum realm.
Exactly. We're talking about the fundamental physical constants, those, unchanging numbers that define nature's laws.
That's right. These aren't just abstract numbers. They are like the universe's basic recipe ingredients.
And specifically the quantum ones, right? The ones critical for atoms, particles, interactions, all that stuff.
Those are the ones, the quantum constants.
Okay, so our mission here in this deep dive is to take your source material and really unpack these constants. What are they? Why these values?
And what are the big mysteries still hiding there? It's fascinating stuff.
Absolutely. Think of this as your shortcut to grasping some really mind-bending ideas about the very fabric of the universe you live in.
So where do we start? Usually with Planck's constant, symbol h.
Right. Your sources give the value, roughly 6.626 by 10 erojoule seconds. Very small number.
Incredibly small. And it goes back to Max Planck, around 1900, trying to figure out black body radiation.
And his big idea was, well, it was revolutionary, wasn't it? Energy isn't smooth, it comes in packets. Quanta.
Exactly. That was the breakthrough. Planck's constant h is the fundamental constant of quantization. It's right there in E equals height.
Energy equals h times frequency.
Yeah. The energy of one photon, one quantum of light, is proportional to its frequency. A total break from classical thinking where energy could be anything.
And it doesn't stop there, right? Wave-particle duality?
Oh, absolutely.
Yeah.
Your sources mentioned de Broglie's idea h is central there too.
Yeah.
Particles have wave properties.
The wavelength equation, Ollie HP.
That's the one. Lambda equals h divided by momentum. It connects the wave aspect, wavelength, to the particle aspect, momentum, using Planck's constant.
And Heisenberg's uncertainty principle uses it too.
It does. H sets that fundamental limit. You can't know both the position and momentum of a particle perfectly at the same time.
Your sources show the inequality. O2. Wait, that's not h, it's h bar.
Yes. Good catch. M is just h divided by 2. Numerically, about 1.054 by 10 Joule seconds.
So why the extra step? Why divide by 2 and use h bar?
It's mostly convenience. It tidies up a lot of the equations you see all the time in quantum mechanics, especially things involving rotation or waves like angular frequency or angular momentum. Schrödinger's equation often uses h.
So h bar is like the natural unit for angular momentum in the quantum world?
Pretty much. Particle spin, for instance, comes in multiples of 8 too. It pops up in commutation relations too, showing how quantum measurements don't always commute.
So it's another sign of that quantum lumpiness.
Exactly. And the fact that both h and h are so incredibly tiny explains why we don't notice these quantum effects in, throwing a baseball.
But they completely dominate at the atomic scale.
They rule the atomic world.
Okay, moving from energy packets to charge, the elementary charge, ETH, about 1.602 by 10 eurocoulombs. Your sources mention Millikan measuring this accurately.
Right. And the key thing about E, as your sources point out, is it's the smallest unit of free charge found in nature.
Free charge?
Yeah, meaning charge that can exist on its own. All the free charges we see are whole number multiples of E.
But what about quarks? Don't they have fractional charges?
They do, like plus 23 or negative through 13. But you never find a quark floating around by itself. They're always bound together inside protons and neutrons because of the strong force. So E is the fundamental unit you can actually isolate.
So charge, just like energy, is quantized. It comes in lumps of E.
You got it. And E determines the strength of the electromagnetic interaction. It's in Coulomb's law, dictating how strongly charges attract or repel.
And that affects everything from atoms to chemistry.
Fundamentally, yes. Atom formation, chemical bonds, it all boils down to electromagnetism, governed by E.
Okay, next up, mass. We have the electron rest mass. About 9.109 by 10 kilograms. Really tiny.
Extremely light. That's its intrinsic inertia, its resistance to being accelerated. It's a key parameter in the standard model.
And crucial for atoms, right? Calculating energy levels.
Absolutely. And because electrons are so light, it's relatively easy to get them moving near the speed of light, where relativistic effects kick in. So M's important there too.
Then there's the proton. Proton rest mass, M. Much heavier, around 1.672 by 10 kilograms.
Right. Protons and neutrons make up atomic nuclei. So M-yours is central to nuclear physics, binding energies, nuclear stability, reactions.
But your sources mention something really fascinating about the proton's mass. It's not just the sum of its parts.
That's the amazing thing. A proton has 3 quarks inside it, but if you add up the masses of those quarks, you get only a tiny fraction of the proton's total mass.
Wait, really? Where does all the rest of the mass come from?
It's mostly energy. It's the kinetic energy of the quarks zipping around inside, the energy of the gluons, the particles carrying the strong force, and crucially, the energy stored in the strong force field itself that binds them together.
Hom incusings in action, inside a proton.
Exactly. Mass is energy. For composite particles like protons, most of their mass comes from the energy holding them together. It's a direct consequence of quantum chromodynamics, QCD, the theory of the strong force.
Wow. Okay, that's, yeah, mind-blowing.
Yeah.
Let's shift gears slightly. The speed of light in vacuum, c, an exact value, 299,792,458 meters per second. We think of c with relativity, but your sources say it's key in quantum mechanics, too.
Oh, it's deeply woven into QM, especially when you get into relativistic quantum mechanics or quantum field theory. C is links energy and mass via EPSOD.
Then for photons, EPC, right, energy and momentum.
Exactly. And since photons are the carriers of the electromagnetic force, c is the speed at which quantum information via electromagnetism travels. It connects space and time.
So it's a unifier.
Very much so. It helps define natural scales when you combine it with h and e's.
Okay, one more. The Boltzmann constant, K or K, about 1.380 by 10 AGO per Kelvin. Your sources call it a bridge between micro and macro worlds.
That's a great description. In statistical mechanics, it connects the average kinetic energy of particles in a gas to its temperature, EAV-G, 32 kT. That's its macroscopic link.
But its role in QM?
It's crucial when dealing with large numbers of quantum particles. Think quantum statistics, Bose-Einstein statistics for bosons, Fermi-Dirac for fermions. K is involved there.
It was there at the start, too, with Planck.
Yes. It appears alongside H in Planck's law for blackbody radiation, the formula that started the whole quantum revolution. It connects energy scales, related to H, to temperature scales, related to K.
So these constants aren't isolated numbers, they're interconnected.
Deeply. And their combinations, as your sources highlight, define other fundamental quantities in natural scales.
It's like the Bohr radius. A, derived from A, electron mass, charge, and that A thing. Permittivity of free space.
Exactly. And the value comes out to about 5.29 by 10^2 meters.
Which is basically the size of a hydrogen atom.
It's the most probable distance between the electron and proton in hydrogen. It's the characteristic length scale for atoms, set by these fundamental constants.
And there's an energy scale, too. The Rydberg energy, right?
Yep. Derived from AE, Ish, and Ish again, comes out to about 13.6 electron volts.
That's the energy needed to rip the electron off a hydrogen atom, isn't it? Ionization energy.
Precisely. It sets the scale for atomic energy levels the light atoms emit and absorb. So the constants determine atomic size and the colors associated with them.
Your sources also mention Planck units, using T, C, and G, the gravitational constant.
Right. Combining those three gives you fundamental units of length, time, and mass.
The Planck length, 1.6 by 10 euro, Planck time. T, 5.4 by 10 euros. Planck mass, M 2.2 by 10 euro. The length and time are unbelievably tiny.
Mind-bogglingly small. The mass is actually quite large compared to elementary particles, interestingly.
And the significance of these Planck scales.
They represent the frontier, the scale where we expect both quantum mechanics and general relativity, GC, to be crucially important simultaneously. It's where our current theories likely need to merge into something deeper, like a theory of quantum gravity.
Okay, let's dedicate some time to one specific constant your sources really emphasize, the fine structure constant, alpha, value around 11,137.036. What makes alpha so special?
Well, first off, it's dimensionless. It's a pure number. Doesn't matter if you measure in meters or feet, coulombs or stack coulombs. Alpha is always alpha.
Universal number, okay.
And look how it's built, according to your sources.
Yeah.
It's got the elementary charge E, the electromagnetic constant air, Planck's constant A, and the speed of light c.
Wow. Electromagnetism, quantum mechanics, relativity, all baked into one number.
Exactly. That's why it's so fundamental. It essentially tells you the intrinsic strength of the electromagnetic force, how strongly photons couple to charged particles.
And its value being small, around 1137, is important.
Very important. It's why physicists can do calculations in quantum electrodynamics, QED, using perturbation theory, basically, treating the interaction as a small effect. If alpha were much larger, QED calculations would be vastly harder, maybe impossible.
It originally explained fine structure in atoms.
Yes, tiny splits in atomic energy levels that weren't explained by simpler models. Alpha accounted for them.
So it's dimensionless, connects major theories, sets a force strength. But what's the mystery your sources mention?
The mystery is why 1137, or more precisely, 1137.035999. Why that specific number? Our current best theories, like the Standard Model, don't predict its value, we just measure it.
We don't know why it has the value it has.
Nope. It's one of the biggest why questions in fundamental physics. Is its value arbitrary? Is it set by some deeper principle we haven't discovered yet? Nobody knows for sure.
Okay, so we call them constants, but your sources hint they might not be perfectly constant. What's this about running values?
Right. That's a well-understood concept in quantum field theory called running coupling constants. It means that the effective strength of a force, like electromagnetism represented by alpha, actually changes depending on the energy scale of the interaction you're probing.
So alpha isn't strictly 1137 everywhere all the time?
At everyday energies, it's extremely close, but if you probe interactions at very high energies, like in particle accelerators, the effective strength of electromagnetism actually increases slightly. Alpha runs with energy.
And this is predicted, expected.
Yes, this running is a solid prediction of QFT, and it's been experimentally confirmed. It happens because of quantum fluctuations in the vacuum around particles.
Okay, but then there's a different idea that the constants themselves might actually vary across space or cosmic time.
Yes, that's a more speculative idea, usually coming from theories beyond the Standard Model. Some theories imagine that what we measure as constants are actually linked to evolving cosmic fields.
So scientists are looking for this. How?
They do. By, for example, looking at the spectral lines from incredibly distant quasars' light that left billions of years ago. If alpha was different back then, the patterns in the spectra would be slightly shifted compared to lab measurements today. Or using ultra-precise atomic clocks to see if their ticking rate changes relative to each other over time.
And any signs of change?
So far, the evidence puts incredibly tight limits on any possible variation. If they're changing, it's by an absolutely minuscule amount, if at all.
But if they were found to change?
Oh, that would be revolutionary. It would be concrete evidence for new physics beyond our current framework. A huge discovery.
So we measure these constants incredibly precisely. They define how the universe works at a fundamental level, but they leave us with these huge questions.
Absolutely. Like the big one. Why these specific values? Is there some ultimate theory, a theory of everything perhaps, that will one day derive these numbers from pure logic or some deeper structure?
Or are they truly fundamental, maybe even random, or derived from something we can't even imagine yet?
Exactly. And how many truly independent constants are there really? Dimensionless ones like alpha seem more fundamental, right? Since they don't depend on our units.
Your sources also brought up the anthropic principle again in this context.
Right. It's the observation that the values we measure seem, well, almost suspiciously fine-tuned for life to exist.
Meaning if they were slightly different, the universe would be hostile to complexity.
That's the idea. Slightly change alpha, or the particle masses, or the force strengths, and maybe stars couldn't form, or carbon wouldn't be stable, or galaxies wouldn't hold together. The conditions for chemistry, planets, life, they seem to depend sensitively on these specific values.
So the anthropic principle suggests maybe we see these values simply because if they were different, we wouldn't be here to observe them.
That's one interpretation. It's a bit philosophical, of course, and not really a predictive scientific theory. But it highlights how peculiar it is that the constants fall within the narrow range that allows a universe like ours and observers like us.
Okay, let's try and wrap this deep dive up. These quantum constants are essentially the numerical backbone of the quantum world.
They dictate the scales, the strengths, the very rules of the game at the most fundamental level we know.
We know their values with incredible precision. They work perfectly in our equations.
But their origin, why these numbers, remains one of the deepest mysteries out there.
So understanding these constants, even just knowing about them, gives you a real window into the cutting edge of physics and the quest for ultimate understanding.
They're like clues left for us by the universe, written into its very fabric.
And maybe a final thought for you, the listener, to ponder. These numbers, 11137, the tiny mass of the electron, the speed of light, they seem so precisely set. Just right for atoms, stars, chemistry, life. For you to exist, is that just luck, a cosmic coincidence?
Or does that fine-tuning hint at something deeper, some underlying principle or reality that we just haven't grasped yet? Something to think about next time you consider the numbers that define our universe.